11.
Are we starting?
Okay, so we're gonna get started. Welcome everybody. I hope everybody here knows who I am at this point in time. I am not going to introduce myself again. So thank you everybody for coming. Today our amazing STORM REU students are going to give their final talks. So they're going to give 10-minute talks about the research they've done with us this summer. There are probably some people listening in online to the live stream as well, hopefully some of your families. So in the essence of time, because this is a lot of talks, I'm going to ask that we limit our questions to just one per student. And if you have follow-up questions, please reach out to them or ask them at the poster session on Wednesday, okay? So again, how is this gonna go? We have an order. I think our students know what that order is. Otherwise, I think we can just go ahead and take it away. So, Austin, are you ready to rumble? All right, welcome. Scott, take some pictures.
All right, hello, my name's Austin, and I had the pleasure of working with Michael Foster and my grad student John Gencio this summer to analyze satellite regional cloud climatology over the Great Lakes using PATMOS X version 6. And to kind of just give you a background about why we studied clouds in the hopes of getting a better idea of, just cloud climatology and the change of weather patterns over the Great Lakes themselves. And to do this, satellite meteorology gives us a better understanding of these particular topics, specifically how cloud patterns change and just the general trend in cloudiness over the Great Lakes. And to do this, we took cloud fraction over the Great Lakes using 40 years of data from the PATMOS X cloud data. And this was to recreate a study done in 2013 over the Great Lakes using a previous version of PATMOS X. So PATMOS X is called Pathfinder's Atmospheres Extended. It is a multi-decadal global cloud record derived from multiple satellites. And that figure on the right there kind of shows you just the different satellites that make up this cloud record. It starts from NOAA 6 and it goes until NOAA 19. And it's got some European satellites, MEDOP-A and MEDOP-B as well, that make up this cloud data. It is a collaboration between NOAA and SIMS, SIMS being the Cooperative Institute for Meteorological Satellite Studies here at the university. And it was created to establish a satellite-based cloud record. And the way that it works is it has two nodes, one descending node that crosses down the Earth in the morning at around 7:30 a.m., and then an ascending node that comes back up across at 1:30 p.m. local time. Around NOAA 17, it added a third node in mid-morning on the descending aspect at 10 a.m. So one of the main focal points was the difference between the previous PATMOS X version and this version 6. So one thing that version 6 added was the high-resolution infrared sounder called the HERS. This gives a better idea of challenging climates when detecting clouds, specifically when there's ice and snow on the ground, any sort of polar climates where it's very cold near the surface, and then at nighttime. So it helps to detect CO2 and water vapor to give us an idea of whether a cloud is actually present at the location being observed. Another main focal point was being able to collocate and interpolate the AVHRR data, which is the Advanced Very High Resolution Radiometer, which actually takes pictures of the clouds on Earth, and being able to collaborate this with the HERS data in a single radiometric record. As well as adding a naive Bayesian cloud mask, which helps to determine cloud phase, whether the cloud is made up of ice or if it's liquid water. And then this is collaborated with the Enterprise cloud mask, which also helps with cloud phase and adding more dimensions, where the previous version had only one dimension and version 6 added a second and third dimension. So getting into the data and methodology, like I said, combining the AVHRR data and the HERS data, and which previous versions of the PATMOS data did not include. So version 6 includes 10 extra years of data on top of the previous 30 years, where version 5.3 was a study done between 1982 and 2012, where version 6 was 1982 to 2023. So we took these cloud fraction data values, which were both diurnally and non-diurnally corrected. And that, if we look at this figure here on the right, each of these different colors determines a different version of the satellite and each different launching of a satellite. So as you can see, as soon as a satellite is launched, it starts drifting in its orbit immediately, where that tends to mess up the local time at which the data, or the satellite, is collecting data. And so when we diurnally correct these values, it makes sure that the data is consistently captured over a local time. And then we unfortunately did not get to look at the wind data to cloud fraction, but something that we hope to view in the future research, where we can collaborate between wind data and the cloud fraction. So the first figure that I thought was important was the mean annual cloud fraction, where this figure here on the left was version 5.3, and the one on the right is version 6. It takes the average of all years in the data set, so all 40 years for version 6 and all 30 years for version 5.3, and it takes the average cloud fraction so that we can see kind of what the cloudiness over the Great Lakes looks like in general. We can kind of tell that there is an increase in cloudiness itself between the two versions, not necessarily because there are more clouds, but because version 6 is more sensitive to detecting these clouds and being able to portray what cloudiness looks like at present time. And so we see a very high cloudiness over the lakes themselves and the northern masses above the lakes, where cloudiness generally tends to stay the same south of the lakes. One figure that was not included in the previous study done in 2013 was the monthly mean cloud fraction, but it was something I thought that was interesting to look at. We can kind of see the general trends in cloudiness between the seasons, where we kind of expect to see the most cloudiness in the winter months, with the highest amount of clouds being over the Great Lakes themselves. And as we progress through the seasons, we'll see less and less cloudiness, with spring decreasing, and then we see the least amount of cloudiness in the summer and fall months. So this is the mean cloud fraction trend, where we can see just general cloudiness and how it decreases over the 40 years. As we kind of look at these, our slope values give us an idea of what cloudiness, how cloudiness changes over the decades. It's about a 1% decrease per decade between these two graphs. This one is 5.3 and version 6. They are generally the same slope trend. The greatest difference we see is the amount of cloudiness, kind of like we've seen in the past figures, where cloudiness starts at about 0.65, and then version 6 starts at a higher amount at 7, but they are decreasing at about the same amount there. Another figure we wanted to look at was the mean cloud fraction trend over land and water. As we can see in the past figures, there was a great difference between cloudiness over the land and cloudiness over the water, and this is something that we wanted to look further into because the Great Lakes are such a big feature on land that we can see kind of how they change weather patterns and cloudiness themselves. And version 5.3 had hourly data, so it was able to split up into 6 hourly intervals, whereas version 6 we only had daily data, so we took averaged data over months. And the greatest difference we can see between water between 5.3 and 6 is the increase in the spring months that we don't really see on version 5.3. It sits about constant at a 0.6, where for the spring months it's at about a 0.8 for version 6. And that's the greatest deviance we see between these two. With land values, we see a higher range of cloudiness, where there's a lot more deviance between having clouds and clear skies compared to over the water. So in conclusion, Patmos X is able to more efficiently detect clouds and portray the clouds themselves. With that, the most important figure being the mean annual cloud fraction, we can see the most difference over the Great Lakes themselves and those northern land masses, where the southern land masses stay generally the same between the two versions. Detection of clouds, land south of lakes, is mostly unchanged, and then general cloudiness trends are both decreasing for both versions, but we see just a slight decrease more with version 6. And any deviations that we see in the data for our cloudiness is most likely due to the added cloud mask for version 6 rather than the extra 10 years of cloudiness. That's all I have for you. Are there any questions? Yes.
Where does the trend come from, like physically?
The trend of cloudiness, it's generally just an actual decrease in cloudiness that we see over the years. Cloudiness itself just globally has been decreasing for the past 40 years. And when we specify that over the Great Lakes, we do generally just see a decrease in overall cloudiness on Earth.
So it's consistent with what we see globally.
Yeah, for sure.
Well, thank you, Austin.
Sweet.
All right. Thank you very much. All right. Hello, everybody. My name is Alejandra Garcia, and this summer I had the pleasure of working with Dr. Daniel Weimon and Aaron Gosh on spatial analysis of extreme nighttime heat events, social vulnerability, and environmental social injustice here in Madison, Wisconsin. So, giving some background on the research that we conducted this summer, we took a 2014 study that showed an urban heat island effect here in Madison, and it showed a spatial relationship between extreme heat, built environment, and population density. We also looked at a study from a different location done in 2013 in Spokane, Washington, which showed strong correlation values between that urban heat island, demographics, and impervious surfaces. So why is that important? It's because extreme heat events disproportionately impact socially vulnerable populations here, and also identifying these high-risk areas will help understand and better support these areas during an extreme nighttime heat event. So what was our objective with this research project? We wanted to identify correlations between extreme nighttime heat events, metrics of social vulnerability, and environmental social injustice here in Wisconsin. And actually this map here is the spatial distribution of those extreme nighttime heat events. You can see that hotspot right here that we use to kind of correlate with these other variables that we will be looking at in this study. And why we focus on minimum temperature is because that nighttime heat stress is very detrimental to your health. When you're constantly exposed to extreme heat events, it can lead to heat-borne illnesses such as heat stroke and affect people with pre-existing health conditions. So the data that we used was from 150 stations across the Isthmus and the Madison area. So they're actually all included in this yellow box right here. That's the extent of where those stations were. And we also used data from the Social Vulnerability Index from the CDC, so that included the socioeconomic indicators that we looked at and also demographic. We also used the Wisconsin DHS Heat Vulnerability Index, which included stuff like health factors that we were not able to get to for the summer. And for that built environment, we looked at the National Land Cover Database and that Multi-Resolution Land Characteristics Consortium, and we compared that to the temperature data we got from these 150 stations that were from 2012 to 2021. That was the data collection for those stations. So how we did that was, how we defined our extreme nighttime heat events was we actually used the Dane County Regional Airport to give us kind of a QC, a basis of what we were looking for. And we defined it as 3 or more consecutive nights where the nighttime minimum was 95th percentile or higher. So these really extreme temperatures and those long periods, those 3 or more consecutive days. And that's how we took that for the 150 stations, and we found the nighttime heat events. And following the Spokane study, we found correlation values between the spatial distribution of those extreme nighttime heat events, socioeconomic indicators, that's from the CDC, demographics, again from the CDC, and built environments, which is from the National Land Consortium. We also had an interview with the Wisconsin Department of Health Services to see what should we be accomplishing with this research project. How can we best serve the Madison community? And how we even made these maps is we used ArcGIS to remap those station data. So we assigned an area with a temperature value, and we overlaid that with the Dane County Census Tract, and we assigned a value to that area. And then after we made that social distribution map, we looked at the social vulnerability factors from the CDC, and we also looked at the HVI, that Heat Vulnerability Index, from the Department of Health Services. So this is a breakdown of what is included in the variables that we looked at. That socioeconomic indicator included people that are unemployed, people living in the 150% poverty level or below, and then for the demographics, we looked at the racial and ethnic minority status, which included ethnicity and race, so Hispanic or Latino, Black, Asian, African, American, Indian, Native Hawaiian, that sort of thing. And then in the Wisconsin Heat Vulnerability Index, again, they included stuff like population density, health factors, demographic, socioeconomic factors, things that we looked at, but they added that extra health factor thing to it that was really important for our research. So what we found is a hotspot on the Madison Isthmus. If you remember that last minimum temperature spatial distribution, you saw that it was really concentrated on the isthmus. We also found that extreme nighttime heat event is correlated strongly with built environment and socioeconomic indicators. However, it is not strongly correlated with demographic status, which is good because that means people, racial and ethnic minorities, are not disproportionately affected by extreme heat events. So this is a table that shows the correlation values. Again, they're correlated with the minimum temperature, that spatial distribution. And we found that areas that are experiencing high highs are also experiencing high lows, so they're not receiving any relief. That's a very strong correlation value. And then it goes with impervious surfaces, again, very strongly correlated with areas that are highly urbanized. Heat vulnerability index, again, if you're more vulnerable to heat, you're also experiencing these high heat events. Socioeconomic indicators, if you're unemployed, 150% poverty line, again, struggling financially, you have a higher chance of experiencing these nighttime heat events. And finally, racial and ethnic minority status, again, that correlation value was not quite there as compared to the other variables we looked at. So getting into our distribution, that spatial heat distribution, again, this is that minimum temperature, that low temperature, 95th percentile, again, really highly concentrated on the urbanized area of the isthmus. You see that really dark coloring right there that has those highest low temperatures. And looking at those same days, the high temperatures, which again are ranging from about 86 degrees Fahrenheit to 92 degrees Fahrenheit, so really hot, you again see that hot spot right there on the isthmus. So they are really highly correlated. These people are not receiving any sort of relief in the daytime or in the nighttime during these extreme nighttime heat events. Getting into heat vulnerability, again, you can see that spatial distribution, that hot spot right there on the isthmus, which again makes sense because it's strongly correlated with these extreme nighttime heat events. Again, same situation for the heat vulnerability index. People that have a higher chance of being vulnerable to heat sadly are in places where you have a higher chance of feeling these extreme nighttime heat events. For the socioeconomic indicators and racial ethnic minority status maps, you can actually see a really interesting sort of deviation from the isthmus. You can see a sort of ring in the suburban areas of Madison where you have the darkest coloring, which again shows that deviation from the hotspot on the isthmus, again, makes sense because they're less correlated. And for the racial and ethnic minority status, it's even less correlated because again, you get that outer ring in these maybe these suburban areas around the Madison area. So looking at a composite of those 150 stations, we actually looked at a identifier on these stations. They either had a U or an R. So that meant they were in an urban area or in a rural area. And what we wanted to look at was to see, on average, are they experiencing higher highs or higher lows? And again, this supported our conclusion, which is that in these urban areas, they're experiencing higher lows and higher highs as compared to the rural areas. You're seeing almost a 2-degree difference Fahrenheit between these areas, which is really significant in the long run. So to summarize our research this summer, we found that there are strong correlation values between maximum temperature and these extreme nighttime heat events, which suggests that these areas that are not receiving any relief during the daytime are also not receiving any relief in the nighttime. We also found that socioeconomic indicators that are most strongly correlated with these nighttime heat events are mainly influenced by those living with a housing cost burden or those living below the 150% poverty line. So these people within that variable are most correlated with those extreme nighttime heat events. We also found that the nighttime heat events have a strong correlation with built environment, so these highly urbanized areas are more likely to experience these extreme nighttime heat events. And while the correlation between racial and ethnic minority status is not significant, which is good, it does not mean that these people are not experiencing extreme nighttime heat events. They're still feeling the same impacts as other people, except it's just not exacerbated by the urban heat island. These are my references, and thank you. Any questions? Yes?
This is a little bit maybe as like something to look at next, but I wonder if you map the heat island with where the unhoused population index is, if that correlates at all.
Yeah, so the socioeconomic indicators sadly did not include that, and because of the constraint of like the summer, it was hard for us to get into that, but that is like something that is so significant in that Wisconsin Health Department like looks at, is that these people that are unhoused are really vulnerable to these extreme nighttime heat events because they're just out in the elements. So that is definitely something we would love to get into for future research.
Thank you, Holly.
Thank you so much. Thank you.
All right, hello everyone. My name is Bella Butcher Salazar, and this summer I had the opportunity to work with the department head on her design and with my grad student mentor, Emily Mather. And so within Design Labs, looking at land-atmosphere interactions, I was looking at investigating the role of small water bodies in regional energy imbalance. So my research overview focuses on the role of small lakes in regional surface energy imbalance, specifically in eddy covariance data, which I will go into later on. And our question of research was, to what extent do water bodies, and particularly looking at small water bodies within footprint areas in flux towers in the data set Cheesehead 19, contribute to and or affect regional energy imbalance. And so the methods I used to analyze the Cheesehead data was first looking at surface water assessments on a land cover map made by previous grad student James Minot, and then also looking at plotting energy transfers using Cheesehead and reflux tower data, specifically focusing on latent and sensible heat fluxes. And so my hypothesis going into this project was to, I hypothesized that unmeasured heat storage in small water bodies contributed to energy imbalance, and so therefore areas with greater percentages of water would have overall worse energy balance. Just to visualize and look at what surface energy imbalance is, it's when surface turbulent energy fluxes are not equal to net available energy, which violates the first law of thermodynamics. So it's a data discrepancy, and so we're looking at what might explain this energy gap and how water plays a role in this. And yeah, our motivation to look at small water bodies is because in research and literature, they are known to be hotspots of energy fluxes and or have greater heat storage than surrounding landscapes. And often this is not reflected in larger data sets, and so that was my main focus. Oops. Okay, so, there we go, okay. Just to show this surface atmosphere energy exchange, it is consisted of 4 different variables. So energy imbalance occurs when net radiation minus ground heat flux is more than latent and sensible heat flux, when in reality it should be equal to, and so that is the gap that I'm looking at. So for this study, I was looking at the Cheesehead 19 study, which stands for, forgive me if I pronounce this incorrectly, Chocobegone Heterogeneous Ecosystems Energy Balance Study enabled by High Density Extensive Array of Detectors, which essentially is a collection of flux towers in northern Wisconsin that use what's called eddy covariance to measure and calculate energy fluxes between ecosystems and the atmosphere. And I actually had the chance to go up to the site and look at a couple of the wetland sites with Anchor, which was pretty cool. So looking at the Cheesehead map of all the different sites, I was looking at what are called footprints, where climatology footprints are defined as the area surrounding flux towers where the turbulent energy fluxes are actually calculated. So you can see there, those are highlighted in red around the different sites. Because of time constraints of my project, I was only able to look at 4 of the many sites. So the sites I looked at were Northwest 4, Northwest 3, Northeast 4, and Southeast 6. And these showcase a variety of different landscape types, one being a lake and the rest being a mixed wetlands and forest. So in order to figure out how much of these footprint areas is water, I took James's map, which is classified as hyperspectral airborne 1 meter water classification map, which is essentially a very high resolution land cover map that separates all these pixels into 5 different classifications, being wetlands, vernal, river, open, and non-water. And so in order to calculate the percentage of water within these sites' footprints, I was considering vernal, river, and open to be water. So once I estimated the footprint area around each site, this is just an example of 2 of the 4 sites that I analyzed, I then was able to calculate what percent of these footprint areas were classified as non-water or water. So as you can see, Northwest 4, which is a lake site, obviously it has a lot more water compared to Northwest 3, which only has a couple of pixels that you can see there. And the rest of the sites also varied in water percentage. The second methodology that I used was looking at the diurnal average heat flux at the 4 different sites. So what I did was I took latent, sensible ground flux, and then also looking at net radiation, and I specifically averaged this just between June and October, so just looking at the summer, and averaged those to create this figure. And then because energy imbalance is highest at midday, I then shortened the time period to just look at 10 a.m. to 12 p.m. And from there I calculated the energy imbalance at each of the 4 sites. So once I was able to put my 2 different data methodologies together, I plotted water percentage against average energy imbalance at each of the 4 sites. Obviously you can see there's like a big difference between NW4, which is the lake site, and the other sites. However, NE4 was also next to a small lake, and that's kind of the next one up, which suggests that my hypothesis was correct. But there obviously needs to just be more data to look at to further validate this conclusion. So, in summary, I subset a land surface map to each of the defined footprint areas of the Cheesehead 19 study, and then I was able to calculate the percentage of water within each of these 4 footprints. And then also I averaged latent, sensible, and ground heat fluxes over the summer to then calculate energy imbalance at these sites. And in conclusion, 2 of these sites supported the hypothesis that small water bodies increase regional energy imbalance. However, further footprint flux data analysis is probably required to validate this conclusion, maybe looking at sites like with more wetland areas or just smaller like rivers and vernals. And so yeah, future works to continue this preliminary study. We could extend this study to include all the Cheesehead sites or other sites beyond northern Wisconsin. And then also looking at the increased specificity in the time frames at each of those sites, because footprints are different throughout the different times of the day. So looking at each of those footprints at the same site can also be helpful in calculating how water influences energy imbalance. And then also things to consider is looking more into energy storage in water bodies and how that affects energy imbalance, and then also just lastly corrections and improvements to current measurement techniques. Here are my references. Oops. Thank you. Anyone have any questions?
Wait on you.
All right.
All right, I'll let you free.
Okay, thank you.
Next up, we have Tara.
Mr. Michael Notaro. Sorry, the text in me really wants to say Notaro. So, but we got to work with CNIP 6 models from global to regional over the Great Lakes region. So kind of to explain what exactly we were doing. So for the research specifically that we did this summer that I did, we were looking at CNIP global models and how well they represent the climatology in the Great Lakes region. But overall, the goal of doing this is to take the evaluations and determine which models we can use to apply for dynamical downscaling to develop climate change projections in this region. So why we are doing this is really, I have to explain the difference between global and regional climate models because there's a huge difference and we really got to understand it. So global climate models, they either don't at all represent climatology in the Great Lakes region effectively. And so regionally, we are able to look at this more clearly and precise and with more detail. So one way of explaining this is for global climate models, it's as if I was looking at this table without my glasses on. I could tell you it's a table, but I couldn't really tell you what it's about. And the regional climate model that we're working towards will be able to use 3D aspects instead of the 1D models that global climate models have, which 3D aspects include circulation, evaporation, heat, moisture fluxes, which is important to consider when looking at climate change. So how I went about this, so instead of showing you all the coding that I had to do, I'm going to just explain kind of the gist. So we had to obtain certain CNIP models with certain characteristics. So first it had to be historical, and then we were looking at it monthly. And specifically, we're looking at precipitation and air temperature. There's many more aspects, but we only looked at these two this time. And then we went and I downloaded 66 models from the Earth Service Grid Federation. And then down here, downloaded observational models from the University of Delaware, 2 models. However, due to some timing and technical issues, I was not able to produce those models. So we're only going to look at the 66 models that I created, and then once I downloaded them, all I had to do was extract the Great Lakes region using the atmospheric resolution from latitude and longitude of the region, and then after that, we look at just the average climatology. So the models originally go from 1850 to 2014, but we were only going to look at 30 years, so we went from 1985 to 2014, and then once you get the average, we had to convert the units so that on the maps it was easier to understand. And so then we just mapped out the Atlantic Ocean, the Great Lakes region, so you could really look at the actual results around the Great Lakes. And then ultimately we evaluate and determine the models to apply dynamical downscaling. So what I have here is all the models that I worked with. These are the 66 models. And then because it's a ton of models, we are only looking at a 5 scale of resolution. So at the top we have high resolution, at the bottom we have low and coarse. And so it ranges from 0.5 degrees to 2.8 degrees. And then we're going to determine out of those 5 which ones would be best to use. So here are some of the maps I created. So here you can see the high resolution, and here is the lowest and the very coarse model. And you can see at the coarse model, you barely get anything. You don't get any details. You barely predict what is going on out in the Great Lakes region. But here you can kind of start to see a little bit more detail. And then for the air temperature, you start to see the cooling effect on the sides, the eastern sides of the Great Lakes, which is important for climate change to look at and what we need more detail in. And so right now we don't really, even what we have right here isn't effective enough to fully represent the Great Lakes just focus around the 0.5 to 0.1 degrees models so that we get a little bit more detail. But with precipitation, you can kind of start to see the lake effect on more on the eastern side of these lakes. So in conclusion, basically, higher resolution is better than forest models. But ultimately, from the models we got, we kind of, for air temperature and for precipitation, really it's best to get 1 degree and 0.5 degree or lower. Anything higher, you really don't see any details in what exactly is going on. So the goal, as I said before, is just to correctly represent the climate change of the Great Lakes region with more detail and more of the physical aspects that contribute to climate change that we're not seeing right now. And then how we go about doing this, kind of the future steps. So like what we did right here is only the first step into getting to that point. So what we did was kind of just create the guide and the boundary conditions that we will then take these outputs from the models we chose, which would be the 0.5 and 1 degree models, and then and use them as boundary conditions to force a high resolution regional climate model. Okay, that's all.
Questions?
Did you see much variation in the precipitation signature within the high resolution models? Were you able to look at multiple ones within the 0.5 by 0.5 box?
So due to timing, I didn't get to look at all the models, but there was a difference.
Yeah.
But I only got to look at the 5, and so I didn't get to go into that much detail. But there definitely is.
Thanks.
Thank you, Kara.
Alrighty, folks. So today we will be looking at the role of water vapor and temperature in the thermodynamics of Caribbean easterly waves. I'm Luke Morin, and over the summer I had the honor and privilege of working alongside Rosa Vargas Martes and Angel Adames Corraliza. First, we must ask the question, what are easterly waves? Well, in short, easterly waves are westward propagating regions of high and low pressure coupled to convection. They typically have a temporal time period of 2 to 10 days, but span over an area of roughly 3,000 kilometers on the synoptic scale of meteorology. Finally, they propagate westward at roughly 6 to 12 meters per second. Next, why do we care? Not only about easterly waves, but specifically about easterly waves within the Caribbean basin. First of all, easterly waves are the primary seeds for tropical cyclonic development within the Atlantic basin. Additionally, easterly waves can be destructive long before they evolve into tropical storms or hurricanes, as evidenced by this tragic event on the left. This was a landslide that occurred in Puerto Rico in 1985, tragically killing 130 people. This was the culmination of days of rain from an easterly wave that was stalled over the region before that easterly wave developed into a tropical storm and would later impact Florida. Additionally, easterly waves contribute significantly to overall precipitation within the tropical Americas. A couple of interesting facts: 60% of tropical storms and minor hurricanes within the Atlantic hurricane basin start as easterly waves, and an even more flabbergasting 85% of major hurricanes in the Atlantic basin originate as easterly waves. Finally, we're specifically looking at easterly waves in the Caribbean because not much has been done as far as studying these storms or these systems. We've looked at African easterly waves, East Pacific easterly waves, and even Indian Ocean easterly waves, but not Caribbean easterly waves. Objective. The objective of this project was to determine the role of water vapor and temperature in the convective development of Caribbean easterly waves. Our overarching research questions. Number 1, does temperature play a role in the organization of convection within easterly waves? Number 2, does water vapor play a role in the organization of convection within easterly waves? And finally, are Caribbean easterly waves moisture modes, mixed systems, or gravity waves? Before we can answer that, we have to know what are moisture modes and what are gravity waves. Well, I've got an answer for you. In the tropics, at the onset of deep convection, 2 processes immediately start to occur. First, you have the gravity wave response, which acts to try to return the tropics to weak temperature gradient balance. The weak temperature gradient balance is the prevailing thermodynamic balance within the tropics and is akin to the geostrophic balance that we observe here in mid-latitudes. The other atmospheric response is the drying of the troposphere through condensation and precipitation. If the rate of drying is greater than the rate at which we are approaching WTG, the system that develops is a moisture mode. If the rate at which we approach WTG is much greater than the rate at which we are drying the troposphere, we have a convectively coupled gravity wave developing. For data and methodology, we took ERA5 reanalysis data from the ECMWF. We looked at this data from 1980 to 2018 during the months of July, August, and September. Our area of interest was the Caribbean, and the variables we looked at were OLR, precipitation, temperature, atmospheric humidity, geopotential, and our horizontal winds. Note that for geopotential and the horizontal winds, we only sampled at 700 hectopascals because that is the level at which the signature for Caribbean easterly waves is most prominent. Next, with our data, we put that data through a 2 to 10 day Lanczos filter. This filter was on the order of 2 to 10 days for the reason of that being the time period of our Caribbean easterly waves. We then put it through an EOF analysis to look for primary structures in the variance of the data. And once those structures were found, we linearly regressed our data onto those structures to generate our linear regression maps. Finally, we ran our data through 2 sample t-tests to try to find correlations between our thermodynamic variables. Here is the first linear regression map. A few things I would like to point out. The signature for the Caribbean easterly wave is very visible here. We have an area of low pressure coupled to an area of enhanced convection, evidenced by this positive precipitation anomaly. Next, we have an area of high pressure coupled to an area of subsidence, or a negative precipitation anomaly. Moving forward, we can see our energy associated with humidity. We specifically graphed the energy associated with humidity because we later on compare this graph to our temperature-related energy, and it's easier to work with these quantities if they are both in their energy form and not just graphing temperature or humidity individually. What I would like to call to attention is how well co-located our humidity anomalies are to our precipitation anomalies. So pick an anomaly, any anomaly, and I'm going to go between this slide and the previous slide, and you will see how well co-located they are. We got blue on blue, we've got red on red. We're in the clear. Moving forward, here are our temperature linear regression maps. Once again, that very, very clear and distinct easterly wave pattern. But what you will notice is that we don't have blue on blue and red on red. When I switch, you're going to notice that these temperature anomalies fall square in between our precipitation anomalies. Right in between. So, moving forward to our correlation analyses, we would expect there to be a high correlation between humidity and precipitation, which we see. We have a correlation of 0.84, which is very nice. Looking at our correlation between temperature and precipitation, we notice that there is a negative correlation, but not only that, that correlation is very weak, meaning that our temperature and precipitation don't really explain each other well. Next, we can see that there's a high correlation between our moist static energy and our precipitation, and we have an astounding nearly 100% correlation between our humidity-related energy and our moist static energy, whereas we have almost no correlation between our temperature-related energy and our moist static energy, indicating that the majority of our moist static energy is coming from our humidity-related energy. Next, we have our Hoffmahler diagram. This is showing the OLR of our Caribbean easterly wave. Lag regressed from -6 days to +6 days. This figure gives us the phase speed of the Caribbean easterly wave, which is later used in a calculation called the N-mode calculation. And N-mode is used to help determine whether or not this system is a moisture mode or a gravity wave. So, checking our moisture mode criteria, here we have the equation for N-mode coming from Adames 2019. Here we can see our tau, the Caribbean easterly wave timescale, is on the order of 7 days. That figure comes from the previous figure that we just looked at. Our tau C, convective adjusted timescale, is 0.87. That comes from the slope of our humidity versus precipitation correlation graph. Then we have C sub P, which is the phase speed of our Caribbean easterly wave, which we saw on the last slide. And finally C, the phase speed of a free gravity wave at 50 meters a second. From this equation, we've got a calculation for our Caribbean easterly wave of an N-mode of 0.19. That is just below the moisture mode threshold. In order to be a moisture mode, you have to be below 0.2. So, evidence would suggest that Caribbean easterly waves are moisture modes. Key takeaways. So, results show that precipitation in Caribbean easterly waves is highly correlated with Q. Tropical moisture anomalies greatly exceed temperature anomalies. And the evidence points towards Caribbean easterly waves being moisture modes. And with that, I digress.
Okay, we got time for one question.
Rudra.
Hi, great presentation. Do you have any insight why the temperature plot and the humidity plot was not matching up, and was it between?
Yeah, so with that, I'm not sure exactly why the temperatures aren't aligning directly where our humidity anomalies are. That's something that I could look further into as we move forward. I know that moving forward, we plan on doing significance testing and statistical significance testing. So I will definitely talk to my mentors about how we could look into that as well.
Thanks.
Hi, I'm Sarah, and this summer I worked on a project where I investigate atmospheric blocking patterns and prediction in SNAP-Seed project models, and I worked with my mentor Stephanie Henderson and our grad student Grant Gilcrease. So, with SNAP-Seed model experiments, SNAP-Seed stands for Stratospheric Nudging and Predictable Surface Impacts Project, and the aim of this project is to investigate the impact of sudden stratospheric forming events on predictability in seasonal to subseasonal timescales. Sudden stratospheric warming events are disturbances in the polar vortex that can be defined as when polar stratospheric temperatures rise by a large amount in a relatively short period of time. For a major event, this usually means around greater than 40 degrees Celsius in 7 or fewer days. The SNAP-Seed project itself focuses specifically on 3 recent sudden stratospheric forming events, 2 of which were in the northern hemisphere, one in 2018 and one in 2019, and one of which was in the southern hemisphere in 2018. So my research goal was to examine the atmospheric blocking patterns using the data that were collected as part of this project. I aim to investigate model variations and the effects of sudden stratospheric forming on atmospheric blocks and blocking predictability, specifically in the northern hemisphere. So, what exactly is an atmospheric block? For those of you who don't know, it can be defined as a large-scale, approximately stationary pattern in the atmospheric pressure field. They can lead to stagnation of weather patterns, hence like the term block. And here I have some nice diagrams of these images from NOAA. The yellow contour lines are the 500 millibar geopotential heights. And up here on the top, you can see this is zonal flow, where the pattern is straight across. Weather and atmospheric systems will follow the zonal flow without any interruptions. And here on the bottom, we have blocked flow. And as you can see through the blue wind barbs here that the atmospheric flow is not straight across, weather patterns here get blocked by this high pressure ridge here and redirected up to the north. This is just an example of a block and its effects on the atmospheric flow and weather. So as I mentioned, I'm specifically investigating blocks associated with the Northern Hemisphere sudden stratospheric warming events. Each of these have 2 forecast initialization dates. One is set to be 3 weeks prior to the surface extreme event onset, and the second one is prior to the onset of the sudden stratospheric warming. So for the 2018 event, that's January 25th and February 8th, and for the 2019 event, that's December 13th and January 8th. I use the methodology from Henderson's 2016 paper to identify blocks observed 45 days after each of these initialization dates. Within these dates, I have blocks that I'll compare the different cases and different SAMC forecast ensembles, separated mostly into these 2 regions, one which combines the European and Atlantic region, and one that's the Pacific region. So as for data itself, I used the SAMC ensembles are from the CNRM CM 6.1 model. The SAMC project has a bunch of different models, and this is just the one that I used this summer. And I compared 4 different types of data. The first one being the ERA5 data, which is the EuroSV analysis version 5 data, and this is to depict the actual atmospheric state at the time of these blocks for baseline comparison. And then I compared 3 SAMC on forecast ensembles as well. The first one being the control, which is the ensemble in which the stratospheric state is nudged to climatology. The second being the nudge, where the state is nudged with consideration to the stratospheric sudden warming event of interest, and free, which is in which the atmosphere is allowed to evolve freely after the forecast initialization. So now I'm going to look at 2 specific blocking cases out of a bunch of different blocks I looked at. I don't know why this got messed up here, but anyway, all of these blocks occurred after the second initialization date, although this first one is not specifically unique to that initialization date. So all of these figures here are the daily average geopotential heights at the 500 millibar level, which are the black contour lines, and the surface temperatures in Kelvin, which are the rainbow shading. I do want to mention that I remade these plots last night kind of late to have only 1 temperature bar, and in that I accidentally made them all be labeled ERI5 data. They are not. The actual ensembles are the ones in the corner. It goes ERI5, control, free, and nudge, and this is the same throughout the entire presentation. So here at first glance, you can see that the pattern is the most similar between the nudged ensemble and the ERI5 data. It's a bit cooler in the nudged ensemble in the northwest, and a little bit warmer in the east compared to the actuality in the ERI5. In the control, it's much cooler in the northwest. Between the ERI5 and the nudge, you can see the similar omega blocking pattern, which is this high pressure ridge with these low pressure troughs on either side. The free and the control don't really seem to depict that same pattern, although there might be some slight ridges in the data. And here is towards the end. This is the very last day of the block. And as you can see here, the nudged ensemble clearly most accurately depicts the block and the block's development in this region, as the free and control are similarly zonal in the area that the block actually exists. However, the nudge data does not really accurately capture the development of this omega block pattern into more of the Rex block pattern, where this high pressure ridge overturns over that trough on the east. However, it is still definitely more accurate than the other ensembles. So yeah, while not perfect in any sense, it's pretty clear that the nudge ensemble most accurately depicted this block throughout its duration. I also have this nice little figure that shows the days in which blocks were actually detected in this region for each model. And as you can see, only the nudged ensemble captures the block that is seen in the ERI5 data, which suggests that modeling the sudden stratospheric warming event is important for the simulation and prediction of this block. I also have the where I plotted the difference in the geopotential heights, specifically between the nudged and the control ensembles, to highlight the difference just between those ensembles, and it's the nudged minus control. And this is again daily averages for the last day of the block. As you can see, the nudge heights are much higher, whereas there's the ridge that is not present in the control data, and lower in the areas of the troughing that are also not really present in the control data, although it does have a little bit of a low pressure region in this area where you can see the difference isn't nearly as intense. So in the control data in the northwest, the heights are lower than they should be, and in the east, the heights are higher than they should be, and that's where the temperatures are warmer than they should be. In the northwest, the temperatures are cooler than they should be. So the control ensemble does not capture a well-formed high-pressure ridge or eastern trough, which could be leading to these unrealistically cold temperatures in the northwest and warm temperatures in the east. So here I have my second case, which is in the Pacific region, and this is a block from February 5th to February 9th in 2019. So here's the very first day of the block, and you can see that pretty much all of the models appear to have some sort of omega blocking pattern in the eastern portion of the region, although this is an assumption for the free data since the block looks to be part of a ridge, but it is cut off by the constraints of this data. The free and control have like a straighter ridge axis in the Area 5, and the nudge, which appear to be a little bit more eastern. But the cool northern surface temperatures that are in the Area 5 data seem to be most accurately represented by the control data on this study. And this here is the last day of the block, and as you can see here, only the nudge ensemble's block seems to persist as long as suggested by the Area 5 data, although the axis does tilt a little westward and doesn't seem to be as well developed. The nudge surface temperatures also appear now to be the most accurate compared to the Area 5 data. So although the first day appears to have blocks in all of the ensembles, the blocking pattern overall seems most accurately predicted by the nudged ensemble, and it might be worth noting on this very first day here that there are these tight contours in the troughs, which are stronger, noted in the nudge data, which might have supported the duration of the block, holding down the ridge better throughout the duration. So yeah, here's again the nudged minus the control geopotential heights, and you can see again there's pretty large differences in the models, especially in this trough right here to the west of the ridge, and the ridging that's over the trough, which really just brings home the idea that this block was much more well-formed near its demise than the nudged ensemble, as the nudge has the significant troughs and ridging associated with the omega blocking pattern in the Area 5. So yeah, in conclusion, both cases highlighted are most accurately predicted when a sudden stratospheric warming event is taken into consideration. But the effects of the control and nudge conditions do vary greatly with each individual block. The nudge ensemble does tend to affect the blocking pattern, but not necessarily by modeling the blocks more accurately than the control in the other blocks that I studied. The events in which the nudge model is the most accurate do appear to be the most common in the European Atlantic region compared to the Pacific region, at least within the data set I studied. But in general, all ensembles tend to vary considerably from the Area 5 data. In summary, more work is necessary to verify and further understand these results, and some of this future work might include testing other models and SAPSI ensembles. And these are my references. Questions?
Anybody have a question? All right, Sarah, you're free to go. Thank you.
Hello everyone, my name is Anthony Mendoza, and this summer I was working on a project with Hannah Zanowski and my mentor, Marissa Trivas, and I was working on a project called A Comparison of Argo Mixed Layer Depth to the CSM2 Global Climate Model. Now, to give some background, the oceanic mixed layer is a near surface layer of the ocean where temperature, salinity, and density are uniform. Now, as a primary pathway of heat, freshwater, and gas exchange between the ocean and atmosphere, the mixed layer regulates ocean circulation, regulates atmospheric patterns, and influences nutrient availability in the deep ocean. So one of the main questions for this summer was that there's a lot of models that exist that can model the mixed layer, and one of these models was the CSM2 Global Climate Model, which provides estimations for mixed layer properties. But we were interested in seeing if there were any biases that existed within this model, and see if we can improve upon those so that there would be less biases. Because there's always some new information that we learn each year that we want to do so that we could actually improve these models. So this would also help us so that we're actually aware of these biases, and then we can create better models of the mixed layer. So for the actual data and methods, what we did is we saw, in order to see how CSM2 was, like how well CSM2 was as a climate model, we needed to compare it to an Argo climatology for the globe. And so for this, there's a definition that I need to give for the Argo climatology, which is that it's made of many Argo floats, which each profile a specific region of the ocean, taking physical measurements like temperature, salinity, and density. And so here on the figure, you can see the profile of what the Argo life cycle would look like. At first, it starts off with deployment, and after from deployment, then it profiles down to the region that actually needs to go, and then it starts to profile for those physical measurements before coming to the surface, and then relaying that information to a satellite, and then so that that can be analyzed by scientists. So comparing the CSM2 and the global Argo mixed layer climatology would allow us to reflect on that accuracy of it. Here you can also see the float deployment in action, where this would be at the first stages of the actual Argo float deployment, where they would first deploy it, and then it would start to go down to that depth needed for the Argo float. So building off of this for the actual data and methods, CSM2 stands for the Community Earth System Model 2, the second version of a model needed for creating these physical models. So the actual data output, though, came from the Ocean Model Intercomparison Project, the second version, which provides regulations and guidelines for oceanic-related data and climate and Earth system models. So now, using this, we use Argo data from January 2000 to March 2021, and CSM2 model output from 1998 to 2018. Although they have a slight difference in years, we did not feel that these slight differences were enough to affect the actual data output, and so we're confident saying that these data from these years aren't necessarily going to be affected, even though it's a slight difference. So now with that, here's the baseline of what the Argo climatology actually looks like. You can see in these figures, in the first figure, the DJF corresponds to December, January, and February mixed layer depth. So MOD is mixed layer depth, and I'll refer to that in the future from now on, like that. So looking at this figure, you can see where the darker color corresponds to a deeper mixed layer depth. You can see how in the North Atlantic, there's a clear darker depth over there, and how in this December, January, and February plot, how in the Southern Ocean, you don't necessarily see as deep of a mixed layer depth. And then with the January, July, and August plot, which corresponds to the right figure, how it starts to invert from a boreal winter and goes to an austral winter, where you actually see that mixed layer depth now in the Southern Ocean and not so much in the North Atlantic. So that's just something to reference, so that moving forward you can actually start to notice like how the CSM2 model did for the differences. So looking at the actual CSM2 model, here at the bottom we created difference plots for the model and the Argo plot. So using the same data from that climatology, we also used the CSM2 model output and then compared the two data to see what the differences were. So on this figure, you can see at the bottom, for the same December, January, and February plot, where a darker red corresponds to an overestimation by the model, and a darker blue corresponds to an underestimation by the model. Those aren't necessarily things we would want to see. We would want to see it more so the wider tinge, which corresponds to an accurate prediction by the model. But we recognize that that's not always possible. But going to this first plot anyways, you can see how for that December, January, February, how in the model for the mixed layer depth, how in the North Atlantic, there's a large overestimation, which corresponds to that red like I mentioned before, and not so much in other areas, although slightly so. And then you can also see it in the other figure, which corresponds to that June, July, August plot, where now in the Southern Ocean, there's an overestimation there, and there's a red tinge that we saw in the previous plot. And so being interested in this, about why is that there's this overestimation, we decided to look more into the North Atlantic just to get more insight into why this was occurring. And so looking at the top figure, the North Atlantic ocean bias, we plotted the Argo climatology data, the CSM2 model data, and their difference for the mixed layer depth over the annual variation. And so what you could see is that for the month starting from January and then ending at December, how towards the end of winter, corresponding to March, which is 4 on the graph, how that corresponds to a largest difference and not accurately reflections by the CSM2 model. So because of this, that's the region that we need to focus on because it's providing too much overestimation and inaccuracies within the model. So that was something that we noted. And so from this, we came to the conclusions that CSM2 overestimates the North Atlantic MOD by 50 to 100 meters in boreal winter and overestimates Southern Ocean MOD in austral winter. So also, the CSM2 model better represents mixed layer depths in both hemispheres with much smaller biases in both regions. And so, why is this important? Well, it's important because by exploiting model biases, this work helps us understand what can be improved in a future model. Now that we recognize, say in the previous figure, where there's a lot of overestimation in the North Atlantic, when we're actually working with this model, we can recognize that there's going to be a lot of biases in that, and so we can compensate for that and be like, well, does this actually correspond to what we would expect in actual data in the climatology? And so that's something that's also useful. And then future work from this can correspond to leading to understanding what processes led to these biases in the CSM2 model so that they can be better corrected. We have some insights into what they are, and I can talk more about those if anyone's interested, but so that's something that we can work on further. We're determining what caused those actual biases in the model. And so just to acknowledge that this work was supported by the NSF Foundation, and here are my references, and are there any questions?
Go for it.
I want to hear more about the processes that are contributing to these biases. You said you have some insights.
Yeah, so if you were to look at the figure where it's looking for the Arctic climatology, you can already notice how with the actual regions where there was overestimation, how that was, so corresponding to these figures, how if you look at where it's overestimated, it's in the December, January, February plot in the North Atlantic, and then in the Southern Ocean in the June, July, August. But those also correspond in the arcoclimatology to where they're already deepest. And so one thing that we think that could contribute to this is the fact that those regions are known to have a lot of ocean convection, which is vertical motion. And so that's something that the model might not be necessarily taking into consideration, or might be overestimating their role within the model. And so that's something that we can kind of play more with and then see how that can affect like the model and future versions.
Thank you.
Okay. Can y'all hear me okay in the back? My name is Ivan Sloan. I work with Dr. Angela Rowe and Ian Carnejo on studying the microphysical process variability within Taiwan's Meiyu and non-Meiyu storms. Our motivation was Taiwan's really rainy. It gets a lot of extreme rainfall very often, and it's difficult to forecast due to that extremeness. So these events can cause like a lot of heavy rain, and they cause these flooding and mudslide events that can really make things complicated. So in my opinion, understanding these processes that lead to that extreme rainfall is a step towards improving forecasting. To briefly give a background on the Meiyu, it is a front not defined by temperature differences, but by moisture and wind differences that lead to extreme precipitation in Taiwan spring into the summer. And looking at the map, you can see Taiwan has a lot of mountainous terrain and really low coastlines. With using that information, the elevation in the terrain would influence the weather. And that begs the question, how do we determine the Meiyu precipitation process differences compared to the non-Meiyu storms, considering terrain elevation? So, to briefly explain precipitation processes, these are small drops here. They rise due to convection, and as they rise, they may collide and coalesce into larger drops, and those that don't pass this line being the melting line, which is the difference between these warm rain processes and the ice phase processes, it may fall victim to convection, which may cause side swimming, which is the smaller drops being lifted or just falling at a different speed than the larger drops. And the ones that do pass that line become ice crystals, which also may collide and coalesce through a process called aggregation and cause aggregates and grapple to form, which are just larger ice crystals basically. And as those fall towards the melting line, those will melt and cause these larger drops to form. That leaves two different types of large drops, those formed through coalescence and those formed through aggregation. And that line's drawn through warm rain versus ice-based processes. And as these large drops continue to grow, some of them can't handle the pressure of them growing, and they burst, causing that little area over there of the breakup, which causes these large drops to burst into many smaller drops. And these ice-based precipitation would be more prevalent in storms over high elevations, so we're thinking specifically the mountains. This is inferable due to there being less room for warm rain processes at higher elevations. So, using the continuous SPAL radar from May 25th to August 10th from the Precip campaign in Taiwan in 2022, we are planning to use this radar data in order to determine any differences in precipitation processes. So the cases that we found that would help our process were an example on May 26th, a storm that at 9 UTC was over the coast, as it shows on that left figure, in that deep purple and pink areas, very heavy rain over the coastline. And when that storm was over that mountain, the same storm at 7:20 earlier that day. And the one on the right shows our example on June 23rd at 6:40 UTC, which is not May related. So, in order to move through this data, we started out with PPIs, which is a completely top-down view using radial radar. And the plan was to use vertical profiles and take them from those PPIs, but during our process, it showed that those would end up being pretty noisy, so it sort of skewed the data. So we chose to grid these PPIs in order to sort of smooth out the data. As you can see on the far right, those are our vertical profiles, and it's much smoother than our originals. And I don't know if you can see it very well, but there's a dot here. This is basically a location that I choose within an area within the storm at points where the reflectivity value is above 45 dBz. And we use two locations within that storm at two different points in time in order to find variability between like spatial and temporal periods of time. And the vertical profiles, that shows height versus reflectivity, but we also use differential reflectivity and differential phase. And outlines into the next one. We use known fingerprinting techniques of precipitation processes. You can see in the bottom right that shows vertical profiles of fingerprints for coalescence, and we used the range from 0.5 to 4 kilometers. I think it's shown on the last slide. Yeah, on over here, around 5 kilometers is where the melting line is. So the area of interest that we were looking at was from 0.5 kilometers to 4. So we used that range in order to determine these, or in order to figure out these vertical profiles. Basically, we just used each point that shows these fingerprints, and that lines up with the coalescence example. And briefly explain these variables. CH is the reflectivity given by the horizontal size of these raindrops here. As you can see, as it gets larger, it gets more oblate, more flat horizontally, and that increases the differential reflectivity, which is relying on horizontal reflectivity and vertical reflectivity. And to briefly explain differential phase, basically that quantifies it quantifies the size and concentration of the hydrometeors within that range. And our first result, or the first result I'm showing, is from our June 23rd example at 640. We saw very high reflectivity and positive differential reflectivity, and it was decreasing just below the melting line. So that determines, or that indicates that there's breakup dominating within that range, and because there's such high reflectivity, that also shows us that there's a lot of big drops just below the melting line, which, as I said before, that would also indicate that ice phase processes were dominating. So, like I said before, these dots each show the basically the change in reflectivity and differential reflectivity from 4 kilometers down to 0.5. And in the red dots show the coastal Mayu case on May 26th, and that's dominated by coalescence processes. Not much variation there. But moving to the mountain Mayu case, it was quite variable. You notice it is still dominated by coalescence processes, but there was that size sorting as we discussed earlier. And the mountain non-Mayu case was even more variable in that it had 2 points that noted some breakup processes, but otherwise there was that evaporation process and balance being sort of coalescence and breakup are sort of happening at similar rates. And these are RHIs, which is basically a snapshot vertically of a line going through our PPIs. And looking at these, you can tell the non-Mayu case reaches much higher up. I mean, going up nearly to 16 kilometers compared to the mountain Mayu case, which the convection doesn't reach much higher than 6 kilometers. And looking at the mountain non-Mayu case, since breakup was the most prevalent process, then we figured that the ice phase processes were much more dominant than the warm rain processes. And for mountain Mayu, the convection wasn't nearly as deep, so the ice phase processes couldn't dominate. And the coastal Mayu case, which was expected, the warm rain process of coalescence was the most dominant. And these are my references.
Question for Ivan.
You're free to go, Ivan.
Still awake? Yes. Almost done. Okay, so I'm Emily Hunt, and this summer, along with Gerald Acton and Dr. Brad Pierce, I was able to examine the influence of meteorology on high ozone and fine particulate matter events in Chilwaukee Prairie in June 2022. So our research question was, how does meteorology influence these bad air quality days in Chilwaukee Prairie? And some of the background knowledge you need to know before getting into this is that ozone is not emitted, but it is created. It is a combination of VOCs, which are volatile organic compounds like formaldehyde, and NOx, which are nitric oxides like nitric oxide and nitrogen dioxide. Those two combined with sunlight give us ozone. And then we also need to understand the lake recirculation, which is where warm air over the land rises and goes over the cool air over the water, which pushes that cool air over the water back over the land, and you get a temperature difference. And some of the data we used to answer this research question was from the Wisconsin DNR, their Enhanced Ozone Monitoring Program, or EOM, and then the North American Regional Reanalysis Data, or NAR, and then we have the Geostationary Operational Environmental Satellite Program, or GOES-16. So here we're looking at Chilwaukee Prairie, and you can see that the Chilwaukee Prairie State Natural Area is right above the Wisconsin-Illinois border. And we're going to be looking at 2 days. Today we're going to be looking at June 14, 2022, and that's our high ozone or O3 event. And then June 15, 2022 is our high PM2.5 or fine particulate matter event. Here's some data from the Chilwaukee Prairie site. We have the 14th and 15th for both ozone and PM2.5. So here's our exceedance day for ozone, and we have our daily AQI at 150, which is our air quality index. And then our daily concentration is 85 parts per billion. And these numbers aren't one-to-one, but they are related to each other. And then if you look over at the 15th, we can see that our AQI is at a 58, and our daily concentration is only 57, only. And then looking at PM2.5, here's the 14th, we have our daily AQI of 55, and then our daily concentration is 14 micrograms per meter cubed. And then again, looking at the 15th, our daily AQI is now 80, and our daily concentration has almost doubled to 26.1 micrograms per meter cubed. Here is the EPA Air Now surface ozone AQI map. And we can see that this is kind of why we did this project, because you can see that the lake shore of Lake Michigan along Wisconsin is the highest in the United States, the worst air quality in the United States on this day. We have our legend over here shows us that we're reaching unhealthy air quality in this region. Here's some, the loop's not playing, that was very loud. Use your imagination, imagine this is a loop of 0Z12Z, or 0Z6Z12Z and 18Z on June 14th. And you can see, we see that this high pressure system forms a little bit more, gets a little more visible, and then we have a low pressure system that occurs up here in southern Canada, northern United States. And we have flow coming from, these are wind vectors, 850 millibars. We have flow coming from the Gulf through Texas up through the Midwest and into Wisconsin. And then here we're looking at 18Z, which is 1 p.m. Central Daylight Time, and we can see, again, here's this high pressure system, a little more formed there with our flow happening. And then we have GOES data over here, and we can see that there is clear skies in Chilwaukee Prairie, and if we recall from the schematic before, we know that sunlight really aids in ozone production. Here is ozone amounts on June 14th. This red line here is 70 parts per billion, and if you exceed 70 parts per billion over an 8-hour average, then you're in an exceedance day, which is just high amounts of ozone, and we can see that the 14th peaks at around 110 parts per billion. So it is well in an exceedance day. And then if we go back, thinking about that schematic, we know that NOx and nitric oxides turns into ozone, or helps aid in the formation of ozone. And we see that it peaks right before ozone starts to rapidly increase, and then again, as it is rapidly increasing, so we can see that our nitrogen dioxide is turning into ozone. Here's a look at the mesoscale meteorology taking place on the 14th. This red line is temperature, this blue dotted line is wind direction, and then green dashed line is wind speed. And you can see that around 9 a.m., which is around when the ozone was increasing that day, we have a drop in temperature that remains throughout when ozone was high, and then it returns to its normal temperature, or what it was before, and then we have a shift in wind direction to the southeast, and then right before we see the shift that the wind speeds increase. And so this is a very clear evidence of a lake breeze present on this day. So now we're going to look at the 15th, and we're going to look at surface PM2.5 AQI map, and we can see that the air quality is pretty bad around like the south mid area of the United States, which is very different from what we saw on the 14th with ozone just concentrated around the lake shore. And And then again, use your imagination and pretend this is a beautiful loop. And we have a similar synoptic pattern to what we saw on the 14th, with winds coming from the Gulf through Texas up through the Midwest and into Wisconsin. And then here again is 18Z. We can see this high pressure system again is over the southeast United States. And then we have clear skies in Chewauquee Prairie from our GOES true color image. This is why we looked at PM 2.5 on the 15th. This is a time series of the entire month of June for 2022. And you can see that the 14th and the 15th are really high compared to the rest of the month for our PM 2.5. So we wanted to examine that and see what was going on. In summary, we saw that our high ozone event was mainly driven by the lake breeze pollution transport, with our high PM 2.5 event being driven by synoptic scale pollution transport. I just want to say thanks so much to Dr. Brad Pierce, Gerald Acton, and everyone at the UW-AOS department for this research opportunity. And I actually was able to go to Chewauquee Prairie State Natural Area, and these instruments here collected the data that I analyzed this summer. And then here we've got our little team, and then Brad being silly, and so thank you.
Thank you, Emily. Questions? No, they're a tough crowd here.
They're asleep. Okay, yeah.
That's right.
Do you know if these are forecasted very well, like these events, and people have a heads up, these are on their way, or is that part of the problem here? Was that a surprise?
Yeah, that is part of the problem. Gerald's actually working on a model to help make this better. But yeah, that's part of our problem. Some of the stuff that we tried to look into to show this lake breeze, it didn't show it. And so yeah, it's definitely room for improvement that I think is being worked on right now. But yes.
Thank you. That was our last one, right? Stephanie is jumping the count right now. So, thank you, Emily. Excellent. We're very proud of everything you've accomplished this summer. Folks, come around again. There's posters on Wednesday. So your burning questions that you have, you can ask at the poster session on Wednesday afternoon. All right, you guys are free to go. Thank you again, everyone. Wonderful.